knowledge session, everyone. The first talk of the session is by Tian Zheng, and it's going to be on Orion, a zero knowledge proof with linear proof over time.
Sure. Okay. Thanks, Chair, for the introduction. And I'm Tiancheng Xie from UC Berkeley, and I'm going to present Orion, zero-knowledge proof with linear proof over time. This is joint work with Yupeng Zhang and Dang Song. A zero-knowledge proof enables a prover to prove some validity of some statement to the verifier without leak his own secret information. And it mainly satisfies these three properties: completeness, soundness, and zero knowledge. The completeness means that honest prover can always pass the verification. And soundness means that malicious prover can only pass the verification with negligible probability. And zero knowledge means that the proof itself does not leak any information about the secret. And zero-knowledge proofs actually started by Goldenwasser, Micali, and Rakov in 1985, and later is followed by Killian and Micali for generic construction. And there are still many following theoretical works. It's also, some of them are also presented here. And since our paper is mainly focused on a concrete instantiation, so we will for the rest of work, the talk, we will focus on the efficient zero-knowledge proof systems. And at 2018, there are many different zero-knowledge proof systems based on bilinear pairing proposed by these people. And these works mainly focus on concrete instantiations, so they got some trusted setup, and all of these works are actually very fast in practice, and some of them are actually deployed in the industry. More recently, there are different more different zero-knowledge proof systems based on more techniques, such as IOP and interactive proofs, or code-based proofs, and MPC-based proofs. So these proofs mainly focus on removing trusted setup and have a better scalability of the prover. So what caused such development of zero-knowledge proofs? It's mainly because there are some many different applications of zero-knowledge proofs, such as there are applications in blockchain. It's called ZK rollups, mainly focus on making blockchain more scalable and more private. And there are many different startup companies focusing on these ZK rollups, which has billions of evaluations. And there are still other different applications. We got machine learning for ZK machine learning for inference, and zero-knowledge proof for program analysis for secret programs, and more, such as ZK middle box for network traffic analysis, Deco for ZK oracles, and so on. Despite all of this recent developments, however, there are still some challenges on the prover's overhead. We mainly categorize all of these protocols into three different categories. And for the first one, they are based on FFT, where FFT itself incurs a log-n blow up. And second category is based on exponentiations, mainly multi-scalar exponentiations. And such exponentiation will cause a log-n factor 2. And there are another line of work where it does not cause any prover overhead if you assume that AES can be done in constant time. However, they they are MPC based, and their proof size is actually linear, and they are not publicly verifiable. There's another line of work which they can actually achieve succinct and scalable proof. It started by Jonathan Bootle at 2017. However, this works actually, most of them are theoretical result, and only GLS plus 21 is concretely instantiable. However, this paper got soundness problem. The soundness actually is 1/40. It's not negligible. So, and there is another line of work is Boolean circuit, which also achieve very efficient linear time proving. And however, in our work, we mainly focus on arithmetic circuit. So we will continue on this line of work, arithmetic circuit work. And here's our result. So we propose a new system called Orion. And the approval time is actually linear here. And we achieve simultaneously, we achieve log square of proof size. And our soundness is improved from 1/poly to all the way to the negligible, based on the new technique called new sampling technique. And here's our list of technical contributions. We build a linear time encodable error correcting code based on the expander code. And all previous constructions are either not practical or they got a very huge non-negligible failure probability. And later, we build our efficient proof from our new expander code based on this so-called circuit code switching technique. So for the rest of the talk, we are going to talk about our technical details. First is the new linear time encodable error correcting code. And so the first question is, why does zero-knowledge proof is related to the linear time encodable linear error correcting code? Sorry, why does this relate to the error correcting code? So because there are many works actually did the following three phases. First, they parse the witness into matrices. And then they use linear time, they use error correcting code to encode this matrix, both row-wise and column-wise. And they may commit this matrix using Merkle tree. For query, I'm going to show you a query example. For query, they're going to first do a random linear combination on this row of code words. And they're going to check different random columns of this code words. So why does this work? What does this work? Because the error correcting code got a distance property, minimal distance property, such that for any two different valid code word, the minimal distance is actually constant. So there are constant fraction of them are different. For malicious prover, if they only change a few entries of the code, so they're going to get invalid error code word. So it will be detected afterwards. And if the malicious prover change a lot of them, actually they may convert it into another valid code. However, it may not be consistent with an initial Merkle tree commitment. So either way, the malicious prover will be detected using based on the property of the error correction code. So, and there are many concrete instantiations of this error correction code, such as rhizome code. However, this rhizome code actually requires FFT, so that's why it's not scalable in our case. Fortunately, there are many different instantiations of zero error correcting code that is linear time encodable, such as the code proposed by the Spielman and Juki Shai and GLS Plus. This error correcting code are all expander-based code. And next, I'm going to introduce the definition of expander and how does this code encode. So here is an example of expander graph. It's a bipartite graph, and all of this code following the following simple diagram, where you just, for each outputting node, you just sum up the input according to these ages. So we conclude that the expander is first a bipartite graph, and it satisfies some expansion property. For example, in this example, if you randomly select a subset of left nodes, you are going to expand into a much larger right node, right set. So, and there are many challenges to construct this expander code. For example, if you try to do some explicit construction, there is actually a paper from 2002. It's however, this paper got some very large constant, actually 2 to the maybe 100 constant, and they require expander to be super large, so the parameters may not be practical at all. And then there is a random expander construction. However, this random expander construction also got some problems. The probability of successfully sampling this expander is actually 1 minus 1 over poly. So you got a failure probability to be 1 over poly n, and you cannot actually distinguish whether we successfully sampled or not. So it's very insecure to directly use random-based expander generation. To solve this issue, we proposed a new technique to distinguish between successfully generated expanders and failed expanders. So our algorithm is based on a density subgraph algorithm, which I will introduce you later why we use this technique. So our algorithm can improve this random soundness to negligible soundness. So now I'm going to introduce why are we using density subgraph algorithm as our black box. So if you look at a correct expander here, and you calculate the density, it will be 9 over 3 plus 8, where 3 is the size of left set, and right set is 8. So a density definition is actually number of edges divided by number of nodes. And if you look at an incorrect expander, for example, here, the number of nodes is actually much smaller because the expansion property is not satisfied. So it will be 6 over 2 plus 3. And you can notice that the density here is much smaller than the density in the incorrect expander. So based on this intuition, you can eventually find that if it's actually an expander, you got a threshold for the density. So if it is an expander, the density must be lower than this value. And if it's not an expander, the density must be higher than this value. So you can actually distinguish whether it's an expander or not just by looking at the density using this algorithm, maximum density subgraph algorithm. And this algorithm can be implemented in polynomial time. It's actually very fast in practice, and we actually implemented our tester in and the code is available on GitHub. And there are some other technical issues where I do not have time to cover. So there are still, in our paper, it's not just trivial expanders, it's actually called lossless expander. And to test this expander, we need to repeatedly subsample the left set and test whether there's a dense graph using density subgraph algorithm, and repeated this process a sufficient number of times. It's actually n log n times. So then we can conclude that this is a lossless expander. And we use a rejection sampling to sample this lossless expander. And since the original successibility of random sampling is already high, it's actually 1 - 1 over poly. So the expected running time of our algorithm is constant. Sorry, the expected number of times is constant. Yeah, so now we have a efficient expander, and we can use this expander to construct our linear error correcting code. So next I will introduce how to construct the zero-knowledge proof from this expander code. Plus, there is another technique called code switching from wrong. Let me remind you about how do we use expander code to encode. First, you parse the witness into a matrix. Then you encode the matrix using expander code. So this step will cause you a linear number of operations due to the encode of the expander code. And this is the commit and encode step. Next, I will go to the verify and query step. So upon a query on this random value R, you are going to answer this query. So the query is actually an inner product query. So you take the coefficient of this matrix and you inner product with this R. So this is a definition of Y. And we got 4 different checks. So first check will be you take a random column and you inner product with R0. For this check, you're going to, if you implement this check naively, you're going to need to transmit the whole column of the matrix. And for this check, you are going to transmit the whole row of the matrix. So basically, if you implement all of these checks naively, you are going to get a O squared in terms of proof size, because you need to at least transmit 1 row and 1 column of the matrix. The cost of the verification is not certifiable. Fortunately, we got the code switching technique. And the code switching technique is, you will notice that this is only O squared fun in terms of the instance size. So you can actually recursively feed the instance into another zero-knowledge proof system based on maybe real-sum code. Since the size of the problem is only square root of n, you can actually use a log-n technique from here. So you construct the circuit using you construct circuit here. The input is the message, and you pass it through an encoding circuit, and you finally get this row, this column. And you simultaneously do an inner product circuit. For example, if we are doing check 1, you can simultaneously do an inner product circuit here, and you got this result. However, the output of this circuit is still large because you still got a lot of code word where the size is square root of n. And you can reduce it by adding a random selector, and you only select lambda number of different entries in this code word. Why does this sufficient? Because it's an error correcting code. Error correcting code has a minimal distance property, ensures that if it's inconsistent with code, is the minimal distance between this correct code and this malicious code is constant. Sorry, the fraction. There are a constant fraction of errors in this committee rows. So if you randomly sample lambda different entries, the probability you hit at least one inconsistent entry is actually due to the minus lambda. So you can just randomly check a subset of these entries, and you get a very high probability of catching malicious prover. So after we apply this, the overall communication complexity is actually log square n dominated by this recursive proof. And now I'm going to show you some experiments on the system. First is our polynomial commitment compared with breakdown. And if you compare with breakdown, we have comparable prover time. Notice that breakdown is GLS plus 21, so it's a reasonable work. And if you compare it with it, we got comparable proof time, and our proof size is actually much smaller than them because they got square root of them in terms of proof size, and we only got a log square. So there is more than 10 times difference between our proof size. And for more comprehensive comparison in terms of general proof systems, we compare our system with Aurora, Ligero, and Breakdown. And our prover is one of the fastest prover here, order of magnitude faster than Ligero and Aurora. And our proof size is actually here. So our proof size is still much smaller than other systems, because we got polylog proof size. And that's all for my talk. And here's a summary. So we construct our system using linear time encodable linear code from expander. And we reduce our proof size from code switching recursive proof. And here is the code. Here is our paper. And you can scan the QR code to get more information about me. And thank you. Any questions?
We have time for one short question. So let me ask one question. So it seems that your bipartite graph testing technique is pretty general. So I was wondering, your expander graph testing technique is pretty general. So I was wondering if you plug it in other existing zero knowledge proof systems, could you maybe quickly comment on how data efficiency would improve?
So can you repeat your last?
So I'm saying that your graph testing technique, it seems pretty generic, pretty general, and it seems that you can plug it in other proof systems.
Yes.
So I was wondering how would, if you could comment on how data efficiency would improve.
Oh, I see. So yeah, we can so since proof systems are actually rely on a higher level description, it's actually rely on the error clean code itself. So we can actually apply our error clean code to other systems directly. Yeah, and we may need the code switching too, because if you directly apply our error clean code, you need to. This error clean code does not have a nice property such as multiplicative property as the rhythm code. So you still need to do some other modifications to achieve succinct proof size, such as what we did in our paper is called code switching. Yeah.
The speaker, once again. So our next speaker is Leonard Brown from University of Aarhus, and he's going to talk about efficient vector OLE and zero knowledge proofs.
Okay, yeah. Thanks for coming. Welcome to my talk on mozzarella. This is a joint work with Carsten, Alex, and Peter, all from Aarhus University. So we are interested in zero knowledge proofs for arbitrary circuits, in this case, arithmetic circuits for rings Z2 to the K. So the prover has some input W, and it wants to prove and convince the verifier that this W fulfills this relation defined by the circuit. So that makes it circuit output 1. We want the usual security properties such as soundness, zero knowledge, completeness. And the question, why are we interested in this setting Z2 to the K? So we are talking about the numbers or the integers modulo the power of 2 with normal addition and multiplication. Other protocols often work over prime field, but we choose to use this ring instead. So on the positive side, the rings Z2 to the K map very well to the data types and register sizes in modern programming languages and CPUs. So that makes it easy to convert existing programs to circuits that we can prove in zero knowledge, or it allows us to reason about programs in a nicer way. And moreover, the implementation can also get more efficient because we get essentially reduction modulo power of 2 almost for free compared to reduction modulo prime. On the downside, Z2 to the K is not a field. So we have 0 divisors. We can't divide by any multiple of 2, and polynomials can have lots of roots. So it's not bounded anymore by the degree. So that means, unfortunately, many common tricks in protocol design don't work anymore. So we have to work around them. The protocols get less efficient. The proofs get more messy. So on one side, Z2 to the K is very nice for the application and maybe for the implementation, but it's not so nice for the cryptographer. Nevertheless, we think it's quite worth it to look at the setting. Coming back to our proof, we're using the commit and prove paradigm, where the prover commits to the circuit inputs, some intermediate values in the circuit and the output, then proves that these these commitments are consistent with respect to the circuit that is computed. And of course, that the output commitment is the desired value 1 in this case. We're using linearly homomorphic commitments, and this gives us already zero knowledge for linear functions. But of course, we want to have arbitrary circuits, so we combine this with a multiplication check. Given 3 commitments to values A, B, and C, we want to prove that the values in these commitments are indeed fulfill the relation A times B equals C. So these 2 steps also correspond to our contributions. First, we show how to more efficiently instantiate the commitments using vector OLE for Z2 to the K, and then we give a more efficient multiplication check in the setting. So in our zero knowledge setting, we have a designated verifier. We have a linear time prover and verifier, and also linear communication in the circuit size. And our main goal is that the overhead of proving this circuit in zero knowledge should be minimal compared to evaluating this circuit in plain text. So both with respect to computation and memory overhead. So we want that it should be as lightweight as possible. So how does these commitments look like? If we had a large field, then we can just use information theoretic max over this field to create these commitments. Here, the prover holds the value x and a MAC of this value x, whereas the verifier has the MAC keys, where delta is some global random key and kx is a value specific key. So due to this format, we have like a linear homomorphic commitment scheme. So we can just add 2 commitments, get a new one, scale it by constant, etc. This method has been used in prior work, for example, in Mac and Cheese, I think last year at Crypto, or in Wolverine. In Z2 to the K, it's a bit more tricky. We have to go to a larger ring, Z2 to the K plus S, where S depends on the security parameter. This is due to we having 0 divisors, and if we multiply something by an even number, bits would be cut off, and that's bad for security. So we need to work in this larger ring, but other than that, most of the commitments work still the same. Note that here we have x tilde as a representative of x, so that it agrees with x on the lower k bits, but we don't really care what's up in the other bits. So how do we get these commitments? We use vector oblivious linear evaluation of vector OLE, which is a functionality, kind of a generalization of oblivious transfer. Here, the prover inputs the value vector x, and the verifier, which is like the receiver in the vector OLE protocol, inputs a scalar delta and another vector k. And then the sender, which is the prover, gets the MAC vector out of it. We can also look at a slightly different variant where all these values are sampled uniformly at random by the functionality. And then we get the chosen input or the sender chosen input variant just by sending some correction values. Note that here delta is chosen from a set z2 to the s, where s is again a security parameter, but the other values live in a larger ring. So this, how to realize the functionality, is the first part of our paper. And in the history, there are a couple of different options how you could do this. One thing would be to use oblivious transfer or homomorphic encryption, but then that would give us a communication at least in a linear and the length of the output vector. And with oblivious transfer, we would also need quadratic communication in the bit size, because we need 1 OT per bit of the scalar delta. And every OT has like vector size bits. So another line of work uses pseudo-random correlation generators, which is defined for arbitrary correlations. And there, 2 or more parties come together and create a short seed, which then later on can be non-interactively expanded to a long correlation. And the important thing here is that the communication cost is sublinear in the output vector size. And many of these constructions are based on the learning parity with noise assumption. However, active security for vector E PCGs have only achieved for fields so far, if you don't consider like generic multi-party computation approaches. Therefore, in this work, we present an actively secure vector E protocol for the Z2 to K setting with sublinear communication. Let's take a look at the LPN assumption. So the idea is that we take a short, uniformly random seed, then we expand the seed or encode the seed with the generating matrix of a random linear code. We add some sparse error vector on top, where in our case, this error vector is a regular error, so it consists of several blocks, and every block has a single non-zero error value. So this whole thing should look uniformly random, like a long uniformly random vector, given that the random matrix is public. So this LPN assumption has been studied for quite a while, and it's mostly used for either bits or larger fields. But here we consider it over rings Z to the K. Now, how can we use it to expand a short vector E correlation to a much longer one? So assume we have a short correlation. Let's say we use the NOT-based protocol to generate this. The costs don't matter that much because we only have to do it once. So they say we have m of these T vector OLEs here in the blue vector. Then we need to generate this noise vector. So we run a so-called single point vector OLE protocol on smaller sizes a couple of times, 1 time for each block in our error vector. And single point vector OLE means that the value vector has a single non-zero coordinate. So this corresponds to the error in the LPN. And then by linearity, we can apply the generating matrix, add the error on top, and we get a long vector OLE correlation out of it. And by the LPN assumption, this looks uniformly random. Now, if we need even more vector OLEs, we can just use up to m of these, or we need to save m of these, and then we can just repeat the process as long as we want, essentially. So this paradigm has been used in recent works, for example, in Wolverine. And we are also using the Wolverine protocol as a starting point to build our single point vector OLE for Z2K. Because the single point vector OLE is really the crucial thing in this whole expansion step, because here we have actually the output size of the whole vector length n, and we want to realize this without having to communicate this much. So essentially, we only want to the communication cost to depend on the number of error coordinates plus maybe some logarithmic factor in the output length. So now, like a quick overview how such a single point vector E protocol can work. So again, we want to have this relation W equals delta times U plus V, where U has a single non-zero entry beta at position alpha. So if we want to distribute some long random value, we usually would use a PRG or a PRF. Now we have two vectors that are almost the same. They differ in only one variable. So we use a punctured PRF here. We can use build a punctured PRF following the GEGM paradigm. That means we have a short, or we have a normal seed, which is the PRF key. We have a length doubling PRG, and then we can expand the seed in a tree-wise fashion. And every path in this tree corresponds to one evaluation of this PRF. Now we want to have a punctured PRF. That means whoever gets a punctured P should be able to evaluate this PRF at all points but one. So we want to remove one of these paths in the tree. And we can do this by giving this evaluating party these blue nodes, which allows it to compute all the nodes below them. So that means all the PRF outputs except the punctured point. We can realize this by using oblivious transfer, like one OT per level, corresponding to whether this red path in the tree goes to the left or to the right. So in our protocol, the receiver samples the PRF key, then both of them talk via oblivious transfer so that the sender selects the punctured PRF key at a position alpha, but the receiver does not learn alpha. So this can be already used to define the whole output of the receiver. So we just take V as the output of the PRF for the indices, and W is the same except for position W alpha. So there's one step missing. We need to set this W alpha correctly. Here we use another base vector OLE, so like a previously generated OLE. And then the receiver can just send a correction value that depends on all the values Vj, and the sender just, or this allows the sender to compute the missing value W alpha. And this is basically the passively secure variant of this single point vector OLE protocol. However, a malicious receiver could attack in two ways. It could feed inconsistent inputs to the OTs, which makes this tree inconsistent and dependent on what index the sender chose. And it can also send garbage for this value delta. And since both of these values are used depending on the coordinate alpha that should be secret, this can lead to leakage later on the noise coordinates in the LPN, which in turn could help the prover to solve the LPN problem with a higher probability. So we need to prevent both of these attacks. Prior work, such as Wolverine, uses a random linear combination in their large field to catch both ways to cheat at once. But random linear combinations over that R2K are a bit tricky because we again would have to enlarge the ring by at least S bits to ensure consistency of the lower S bits. So for one iteration, that would be fine. But if we want to iterate this vector OLE expansion protocol again and again, then we would have to start with a really large ring that shrinks a bit in every iteration. So that's a bit annoying. So we chose a different approach. First, we use the universal hashing-based trick to ensure consistency of the GGM tree, following like a similar trick from Boyle et al. So we add another layer to the GGM tree. And now all the left leaves will be our outputs as before, but all the right leaves we will feed into a hash function that the sender selects, and the verifier just responds with a hash. And this makes sure that it cannot create an inconsistent tree. So this prevents attacks against the GGM tree. And for the second attack vector for the D, we use a binary linear combination after all. However, binary coefficients, well, you can guess a single coefficient with probability 1/2. And if the malicious receiver guesses the coefficient chi alpha, then it can effectively bypass this check. We say, okay, this is fine, but we compensate for this potential leakage by increasing the overall noise rate. So our ideal single point vector E functionality is not as ideal as we would like, but we can compensate for this leakage. Okay, how can we use this vector E to, or how can we use these commitments that we just created to get zero knowledge for arbitrary circuits? So this check we call Quacksilver. It is based on a prior work Quicksilver. And to remind you of what we want to do, we have 3 commitments A, B, and C, and we want to verify that A times B equals C. So the authors of Quicksilver observed that if you take the MAC equations, multiply them in a clever way, then you get an equation that is quadratic in the verifier's key delta. And here on the slide, all the blue values are known by the provers, and the green values are known by the verifier. And what is important, if the prover is honest, then this first coefficient here, like the coefficient of delta squared, should be 0, because then C is equal to A times B. However, if it tries to do something fishy, then this might be a non-zero value. So we have a quadratic equation, otherwise it's linear. So in a normal way, the prover would just send these first 2 values to the verifier, and then the verifier checks this equation. And if we want to check multiple multiplications in a batch, we can use a random linear combination, which is fine in this way because we don't have to like repeat it over and over. So what if the prover tries to cheat? Well, essentially cheating corresponds to choosing a quadratic polynomial, where the first coefficient is the error that is induced here. So it has to be non-zero modulo 2 to the k. And now the check passes if this polynomial has a root at position delta. Since delta comes from a very large set, this should be very unlikely because the prover doesn't know anything about delta. And yeah, as I said, the polynomial has degree 2 if the prover tries to cheat. Over the field, everything is fine. We can say P has at most 2 roots, so soundness error is 2 over Q, which is still negligible. However, in a ring, we can have many more roots. So in this particular setting, we bounded the number of roots by something like 2 to the k, 2 to the s over 2. So the square root of all the possible values can be roots in the worst case. Hence, we need to use a larger ring overall, and then we end up with something like 2 to the k plus 2s plus 2 log s plus 3. But overall, this is still better than previous solutions. Yeah, we have to live with it, I guess. Before I summarize, I want to leave a few words about the performance. So we implemented this both protocols in the Swanky MPC framework, and for like 64-bit arithmetic, 64-bit integers, you need to work over a 162-bit ring to ensure that you get 40 bits of statistical security. So for large batches in a LAN setting, we can generate roughly 20 million vectorials per second. And then for each vectorial E, we have to send about a single bit. This gives us performance very similar to Wolverine, which did essentially the same work over fields. For the Quacksilver zero-knowledge protocols, we have to send one single ring element of this larger ring per multiplication, because we have to commit to the output of the multiplication. And this gives us a performance of about 1.3 million multiplications that we can check per second. If we take a look at what performance the Quicksilver authors achieve, then their number is about 5 times larger. But they have, I think, a prime of size 61 bits, which means you can't really emulate 64-bit arithmetic. So if you have two arbitrary 64-bit numbers, the result will be 128 bits, and then you would have to do the reduction. So to emulate this kind of arithmetic, you would have to use a larger prime, which in turn leads to more communication and more expensive arithmetic, as we already have in our Z2K ring. In contrast to them, we don't have to care about modular reduction, modulo 2 to the 64. It's just built in natively. Okay, to summarize, we constructed an efficient and practical vectorial E protocol, with active security and sublinear communication, and we only have to send like a single bit or a bit more depending on the parameters. Moreover, we have a new check for verifying multiplications modulo Z22K, and there we only need to send a single ring element per multiplication. But we have still some open questions. For example, this larger ring we have to work in. Can we reduce the overhead of the ring size compared to the K bits we're actually interested in? Depending on the protocol, we have to work in larger or smaller rings, but we always have this kind of overhead. And then many recent protocols for fields use like fancy polynomial tricks or use some code properties. But all these, or many of these techniques don't work anymore for rings. So can we get something similar efficient in the Z2K setting? So if you're interested in more of Mozzarella, take a look at our full version or ask us now or later. And yeah, thanks. That was it for me.
Are there any questions? If there are no questions, let's thank the speaker again. And all right, so the next talk is by Abraham Kothapalli from CMU on NOVA, recursive zero-knowledge arguments from folding systems.
For a new notion known as folding schemes. Oh, that's better. Yeah, and this is joint work with Srinath Sethi and Iana Ziala. Okay, so our goal is to design practical ZK snarks for recursive computation. And what I mean by this is that we want to design a succinct, non-interactive argument of knowledge that allows us to prove that a non-deterministic function f applied n times to some initial input z0 results in some output zn. And I say non-deterministic because we want to allow f to take additional witnesses along the way. Now, this can be instantiated to derive various cryptographic applications and primitives, right? So just by instantiating f correctly, we can derive verifiable delay functions, we can derive zero-knowledge verifiable virtual machines, and we can even derive ZK rollups, which allow us to prove that many transactions to a blockchain have been updated correctly. Now, I hope with these applications, I sort of intuit that we no longer really care only about the theoretical properties of recursive proof systems. We also care about how useful they are in practice and how fast we can get them to be for real-world applications. Now, you might think, okay, well, there seems to be a naive approach here, right? Well, we can just take the function f, apply it to itself n times, throw it all into an arithmetic circuit, and then just prove that unrolled statement using your favorite snark. Okay. While this approach nominally works, the key issue is that this fixes n ahead of time, which means that for certain applications like virtual machines, where the number of recursive iterations might actually depend on the input program, this actually will not work. And moreover, if we can somehow make it work, we still have that the prover memory and the verifier preprocessing time are dependent on n. And depending on the snark that we're using, we might even have the situation in which the verifier time depends on n. So to get around these issues, back in 2008, Valiant introduces this notion of incrementally verifiable computation. Now, the core idea of incrementally verifiable computation is that, well, we can write a proof for a single iteration of f, but then later come back and very cheaply update this proof over time as we keep incrementing the applications of f, okay? And the core challenges of IBC are that, well, we want to be able to arbitrarily increment as many times as we want, and this allows us to recurse indefinitely. And the second core challenge is we actually want to make sure that these proofs don't grow in size as we keep going. Okay, and these two challenges make IBC a difficult primitive to achieve, both in theory and in practice. So Nova is a built ZK snark for recursive computation, which uses IBC as a core building block. So specifically what we do is that we design a very efficient implementation of IBC using this new notion of folding schemes, okay? So specifically at a very high level, a folding scheme allows you to reduce the task of checking 2 instances in a relation to the task of checking a single instance in that relation. And we show that if you have a folding scheme for an NP-complete relation, then you could derive an IBC scheme, okay? So specifically, we designed a new characterization of NP called relaxed R1CS, which is designed to be very quickly and efficiently folded. Now, putting all of these techniques together, we get IBC proofs which are linear in the size of the function f, and they in no way depend on the recursion depth n. But suppose we wanted even more efficiency guarantees in practice. Well, we then show that we can actually add a layer of succinctness and zero knowledge on top of our IBC proofs. So specifically what we do is that we first design a ZK snark for relaxed R1CS, and then leverage this ZK snark to design a very efficient proof that proves the existence of a valid IBC proof, okay? And using these techniques, we're able to go from proofs that are linear in the size of the function f to non-incremental, but very short proofs that are logarithmic in the size of the function f. Now, Nova, putting everything together, represents one of the fastest and one of the most efficient proof systems for recursive computation. So Nova is implemented in Rust in about 6,000 lines of code and is available on GitHub. And we feature the smallest per step prover time, which is just dominated by just 2 multi-exponentiations per recursion step. And our recursion overhead is also the smallest in the literature. Now, what I mean by recursion overhead is that because of how these systems are built, we end up having to prove the function f as well as a little bit of additional overhead. And this additional overhead, in our case, per recursive step, is just 2 scalar multiplications. And finally, using our proof succinctness techniques, we're able to get down the proofs down to logarithmic in the size of f. And roughly, if we're able to represent the function f in about 1 million constraints, then we can get proofs that are 8 kilobytes in size. So today, specifically, I'll be talking about the theoretical backbone of Nova. So specifically, I'll be talking first about how we can use a folding scheme for NP and use that to imply an IBC scheme. And then after that, I'll actually go ahead and develop a folding scheme for NP by developing a folding scheme for relaxed R1CS. So before I begin with our own approach to IBC, it's important that I intuit the original approach to IBC as well as more modern approaches to IBC to intuit how our solution works, okay? So Valiant's original approach to IBC was actually very, very elegant. So the core idea is that, well, let's not only prove the function f, but let's also prove a little bit extra, okay? And let's represent this little bit extra in the function f as a large circuit, f prime, okay? And this little bit extra is going to be a snark verifier that verifies that there exists a snark that proves all prior iterations of the function f prime, okay? And then we can say that, well, to increment this proof, we can write a new proof about this latest circuit, okay, f prime, and call that pi I plus 1. Now, specifically what pi I plus 1 is attesting to is that, well, the function f was run correctly. And also there exists a proof of all prior iterations of the function f prime. Okay, and what this means is that pi I plus 1 really is a proof for I plus 1 iterations of the function f prime. So essentially, we have converted a proof of I iterations into a proof of I plus 1 iterations. Now, Valiant's approach is incredibly insightful in theory, but when we actually try to instantiate the pieces in practice, it turns out that it's quite inefficient. Okay, so the core goal when we're trying to instantiate these objects in practice is that we want to make sure that the overhead over the original function f to derive this function f prime is as small as possible. Okay, so BCTV actually go through the process of instantiating Valiant's approach using the most efficient snarks in practice today, which are these snarks with a constant time verifier that rely on pairings. But they show that to make this even remotely possible in Valiant setting, we actually need to use very expensive cycles of pairing-friendly curves, okay? And also, because these snarks rely on a trusted setup, the IVC scheme itself also inherits this trusted setup. All right, so you might say, okay, well, maybe we can get around these efficiency issues by using snarks without trusted setup, right? But the core issue here is that those snarks actually have verifiers which are not constant time. They actually are more asymptotically expensive, and they actually incur very large overheads over the original function f, okay, which goes against our goal of trying to minimize this additional overhead. So for the longest time, Valiant's approach was considered just of theoretical interest until very recently, in 2019, Bao, Green, and Hopwood introduced a new approach, okay, in which they say, well, let us not only, let us not check the entire proof in the circuit, okay? Let's specifically only check a very small part of it and then defer the rest, okay? And essentially what this allows them to do is avoid having to implement a bunch of very expensive snark machinery like pairings and things like that in the circuit, okay? And this makes that they avoid cycles of pairing-friendly curves, and they also avoid this trusted setup. So a little bit more into detail, what they do is that, well, they design something called an accumulator, okay, that allows you to take that proof and check a little part of it, and then defer the rest of it into that accumulator. So this accumulator doesn't keep growing in size over time, okay? But checking this accumulator is equivalent to checking all the proofs that were deferred into it. Now, to increment this proof or complete the recursive cycle, essentially what they do is they say, well, we can write a new proof which attests to the latest execution of f, and also attest that this accumulator was built correctly. Now, more recently, Buns, Chiesa, Lin, Mishra, and Spooner introduce a technique where they say, well, this proof doesn't even need to be succinct, okay? And what that does is that affords them to make it even cheaper in the circuit, okay? Their proof machinery is even cheaper, and they use even less additional gates of the original function f, okay? So these results in general bring us a lot closer to practice, okay? Because we're really just throwing out as much proof machinery as possible from the internals of the circuit, okay? But the core issue is that, well, we looked at this and we said, well, maybe there's a way to make this even cheaper in practice, okay? And to answer that question, we said, well, okay, where are the costs here? And it turns out that, well, even partially checking this proof in some of these proof systems is quite expensive, okay? And generally, even generating these proofs is also both concretely and even in some cases more asymptotically expensive, okay? So then we said, okay, what if we get rid of the proof abstraction entirely, succinct or otherwise, just completely get rid of it, okay? And we say, what if we only talk about claims, okay? So specifically, what we want to do is say that suppose we had a claim that just talks about the correct execution of the last instance of f, and another claim that talks about the correct execution of all prior instances of f prime, okay? Well, then suppose we had a magic black box that could reduce two claims of the same structure into a new claim of the same structure, okay? Now, this new claim of the same structure essentially attests to both prior claims, okay, because checking that is equivalent to checking both prior claims according to this functionality. Then, essentially, it could be the case that checking this new claim is a lot cheaper if we just create this just right, such that these claims don't grow in size over time, and the corresponding witnesses for these claims also don't grow in size over time, okay? And now, using the analog of prior approaches, we can also increment this claim by just writing a new claim about the correctness of the latest iteration of this computation f prime. And together we can go from a claim of I iterations of f prime into a claim about I+1 iterations of f prime. Okay, well, now the burning question is, how do we actually implement this fold functionality? Okay, and specifically, we need to be able to reduce claims, preserve their size, and also make sure these claims are powerful enough to capture NP constraints, because we actually want to capture any arbitrary function f prime. So to do so, we actually start with a simpler goal. And our goal is to say, well, let's just try to derive an interactive analog of this first. Okay, and then we can maybe use standard techniques to compile this down into a non-interactive version. Okay, so what we do is we derive something called a folding scheme. Okay, so folding scheme concretely reduces the task of checking two claims U1 and U2 into the task of checking a new folded claim U. So syntactically, what this means is this is going to be an interaction between a prover and a verifier, okay, in which the verifier takes as input two instances to be checked, and the prover takes as input the corresponding witnesses. Now they interact a little bit, and eventually the verifier outputs a new folded instance, which is satisfied with, it says it's going to be satisfied with being checking in place of the original two instances. And the prover outputs a new folded witness, which presumably satisfies this folded instance. Okay, so we can derive naturally the completeness and soundness properties for this. Okay, so specifically, completeness is that, well, if the two input claims are valid, then we should have the output claim is also valid. And for knowledge soundness, we must have that, well, if the prover is able to maliciously output a W, or a witness, that satisfies the folded instance, then it must have known the two input witnesses that satisfy the two input statements to the verifier. And one very important piece is that we also have a very critical efficiency requirement. Okay, that is, we want the verifier's cost of interacting in this folding scheme to be significantly less than just directly checking these instances, or even checking one of these instances. Okay, and one other key piece that I need to mention here is that, well, if we have a folding scheme that is public coin, that is, the verifier only sends randomness to the prover, then we can just use the Fiat-Shamir transform to make it non-interactive. Okay, and now putting all the pieces together, essentially, if we have a non-interactive folding scheme that is powerful enough to encode NP relations, okay, then f prime can verifiably fold the two claims UI and capital UI into a new claim, capital UI. Okay, now you might notice, well, this isn't quite like that fold functionality that we had before, right? Because this folding verifier actually needs additional hints to fold this these claims, okay? And these hints are in the form of the transcript from the non-interactive folding scheme. Okay, so specifically, the overall IBC prover along the side runs this folding verifier and keeps track of the witnesses corresponding to these claims. Okay, so it seems that we're getting really close to our final construction, really like we went from IBC to requiring just a folding scheme for NP, okay? But now how do we actually construct a folding scheme for NP complete relations, okay? Well, we have many options, but we'll start with R1CS, which is a very elegant algebraic way of looking at NP constraints, okay? And we can try to use some algebraic properties to very cleverly try to fold two R1CS instances, okay? So recall that an R1CS statement consists of constraint matrices A, B, and C, which represent the computation itself, and a public IO vector X, which represents the inputs and outputs to that computation. Now, a witness, which is a vector, which might represent the computational trace, say, is satisfying if for a new vector Z, which is equal to WX1, we have the AZ times BZ is equal to CZ. Now, I'll say times here to mean the Hadamard product. Okay, that means we're doing entry-wise multiplication, and we're checking each entry. Okay, well, now we have this relation. Let's try to fold it. Okay, so suppose the verifier takes as input two statements with the same computational structure. It turns out this is enough for IBC. Okay, so ABC X1 and ABC X2. Okay, and the prover takes as input the corresponding witnesses W1 and W2. Well, we can try to use the bluntest tool available to us. We can just try to take a random linear combination. So what the verifier does is send over a challenge to the prover, which is just a random field element. And together, they just take a random linear combination of the statement X, okay? And then the prover also takes a random linear combination of the witness. And together, they output the new folded instance witness pairs. Now, the question is, well, does this satisfy completeness? That is ABCX satisfied by that new witness W, okay? And it turns out, unfortunately, it's not, okay? So, letting Z be the folded vector Z, that is Z1 plus R times Z2, okay, where Z1 is equal to W1 X1 1, okay? We have the AZ times BZ is not equal to CZ, okay? And intuitively, the reason for this is, well, just expanding out CZ, we have that it has this very nice purple term and this yellow term, okay? But if we try to expand out AZ times BZ because of that Hadamard product in the middle, we end up having these annoying cross terms highlighted in red, okay? So, and not only that, we have that the yellow piece is also scaled by R squared instead of just R, right? So it seems like there's no hope of both sides of this equation actually to be equal, okay? So our core intuition was to say, well, what if we extend R1CS itself just enough that we can sort of handle all these additional garbage terms that show up, okay? So what we do is that we first introduce a new error vector into the statement E, okay, which is designed to absorb all these additional cross vectors in the middle, okay? And then we introduce a scalar U, which is designed to absorb the additional R squared factor at the very end, okay? So specifically, we're going to define a variant of R1CS called relaxed R1CS, which is just like an R1CS statement, but additionally contains the error vector E and the scalar U, okay? So specifically, a witness vector W is satisfying if for Z is equal to WXU, we have the AZ times BZ is equal to U times CZ plus E. Now, it turns out that this statement is structured just right so that when you take two statements of this form, you can define a folding operation that allows you to get a single statement of this form. Okay, and I want to give you some intuition for why that's the case. So specifically, we're going to design a folding scheme for relaxed R1CS, which is almost right, and I'll fix a few caveats here and there in the next slide. So I only want you to focus on the pieces highlighted in yellow, which represent the changes from the original folding scheme for R1CS, okay? So specifically, now the verifier also takes as input E1, U1, and E2, U2, okay? So now, using its witnesses, the prover computes all the cross terms, okay, including these new U terms that we've introduced, okay, to send over to the verifier, requesting it to encode it into its new error vector, okay? And now the verifier sends back a challenge and computes U and X in a sort of expected way, just taking a random linear combination. But now the prover and the verifier compute the new error vector, okay? And it's computed in a way that accounts for both the old error vectors as well as all the new cross terms that we've produced in this folding procedure, okay? And this is essentially what allows us to balance both sides of the equation, okay? And of course, the prover computes the witness as expected, and together they output the new folded instance witness pairs, right? So it turns out that we can show that this satisfies completeness. Okay, but we haven't said anything about knowledge soundness just yet, okay? So specifically, it turns out that, well, after the prover sees the verifier's challenge, it can try to do some trickery to try to compute a W that satisfies this folded instance without even knowing satisfying witnesses W1 and W2 for the original two instances, okay? So essentially, what this boils down to is the verifier can't actually enforce that the prover is trying to create W as a random linear combination of its two inputs, W1 and W2, okay? And the other issue is that, well, because E is linear in the size of W, just because of how these dimensions work out in the relaxed R1CS statement, we have that the verifier is not even succinct. Okay, so we could have gotten away with the prover just sending over the witness, and that would have been a more efficient folding scheme. Okay, so how do we get around both of these issues? right? And here we introduce succinct, additively homomorphic commitments. Think the Peterson scheme, okay? So specifically the core idea is, well, instead of exposing the verifier to both these error vectors, we're just going to expose it to commitments to these error vectors, okay, which are succinct and small. And instead, the prover is going to hold on to these error vectors in its own witness, okay? And moreover, we're going to allow the verifier in the statement to have commitments to these two witnesses, okay? And this allows the verifier to force the prover to compute the new witness as it chooses, okay? So specifically what happens is now the prover, just like before, computes the new list of cross terms, okay? But instead of sending them directly, sends over a commitment to these lists of cross terms, okay? And now the verifier sends back a challenge. They compute X and U as expected. And then the verifier now computes the new commitments to W bar, and E bar, okay? And because of the way the verifier computes these new commitments, taking advantage of the additive homomorphisms, the prover is forced to compute its witnesses and W and E in just the right way, okay? So together, they output the new folded instance witness pairs. Now in our paper, we show that, well, this satisfies completeness, and this also satisfies knowledge soundness, okay? And moreover, notice that if that commitment right there is zero knowledge, or sorry, is hiding, then we can achieve zero knowledge for this scheme right here. Okay, so this concludes our entire development. We've essentially developed a folding scheme for NP over instances with the same structure because we've developed a folding scheme for relaxed R1CS. Okay, so in summary, now working bottom up, essentially what we've done is that we designed a folding-friendly variant of R1CS called relaxed R1CS. We then show how to develop a folding scheme for relaxed R1CS that's highly efficient. Okay, and then we use this folding scheme to develop a highly efficient IVC scheme. And because we cared about making each of these steps as practical as possible, we achieve a recursive ZK snark with state-of-the-art efficiency. Thank you.
Are there any questions?
Hi, thank you for the great talk. Yeah, I have a question. So instead of doing the recursively and sequentially, have you considered doing, for example, a wide version of the computation, such as a data parallel computation? Does this scheme also work?
Do you mean like more like tree-based recursion
Yes.
topologies? Okay, yeah. So folding actually is very specifically designed for this straight line path stuff. It turns out that when you try to extend folding algebraically for tree topologies, maybe you end up with these quadratic blowups. There are other schemes out there like accumulation schemes, which might be better designed for tree-based structures.
I see. Thank you.
Yeah.
Speaker, once again. The last talk of the session is by Xiao Lang from Rice University on a new approach to efficient non-malleable zero knowledge.
Hello, everyone. I'm here to share this result. Let me start with the definition for non-malleable commitment and non-malleable zero knowledge. For non-malleable commitment, we care about the so-called man-in-the-middle execution of a commitment protocol. And it has two parallel sessions. You can think it in this way. In the left session, the honest committer is talking to the man-in-the-middle adversary. The honest committer commit to some message M. And in the right communication, the man-in-the-middle adversary plays the role of a potentially malicious committer, but he's talking to an honest receiver. And the goal of non-malleable commitment is to make sure that the value committed by the honest committer in the left and the value committed by the man-in-the-middle adversary in the right, these two values should be essentially independent. So how do we want to capture this requirement formally? We will care about two values in the man-in-the-middle execution. The first value is just the man-in-the-middle's view. The second value, M tilde, is the value, you can think it as the value statistically bound in the right communication. For simplicity, let's focus on statistical bounding commitment scheme for now. And in this world, we care about the distribution of this tuple. We compare it with the so-called simulation world. In this world, we just replace the whole left session by a simulator. And this is a little bit different from zero knowledge. This simulator, it cannot rewind the honest receiver because the receiver is honest. But it could run the man-in-the-middle adversary internally and potentially rewind him. So well, our requirement for this simulator is first one is standard. We just require it to be efficient. But importantly, this simulator doesn't know the value M, which is value committed by the honest committer in the man-in-the-middle execution. And we say that the protocol is non-malleable if this simulator, if there exists such a simulator that is able to output a simulated tuple that is indistinguishable from the one coming from the man-in-the-middle execution. So here the intuition is whatever the man-in-the-middle can do in the real world with the help of the left honest committer now can be done by an efficient simulator. In this way, the value committed in the right session should be independent of the value committed in the left session because this simulator doesn't know this M at all. So if I just put the definition in this way, actually, this definition is impossible to achieve because there is a very trivial but hard to deal with attack. So let's say the man-in-the-middle just relay the message from the left to the right without any modification. So in this setting, you can see that the value committed in the left M and value committed in the right M tilde, they will be always equal. This is a non-trivial relation. Now they are dependent on each other. However, you will never be able to simulate that in this world because this simulator has no information of this M at all. So this is something like, I think this is a definitional issue. Like no matter how hard you try, as long as you set definition as the previous one has shown you, you will never be achieve this definition. So to deal with this issue, actually, we will only focus on something called identity-based commitment, or someone call it tag-based commitment. This commitment scheme, you can think in this way. For every execution of the commitment scheme, there is a ID or tag integrated in the communication. So if you want to copy the communication, just like the trivial adversary I described earlier for information back and forth, then you are bound to copy the ID. And this can be done like if you have one function, you can easily make a commitment scheme to be identity-based. So our eventual definition is that we focus on identity-based commitment scheme, and we only have this requirement condition on left session ID and right session ID are not equivalent. Okay. Now with the definition of non-malleable commitment in mind, it's now easy to understand definition for non-malleable zero knowledge. So instead of consider the man-in-the-middle execution of commitment scheme, we consider that for the zero knowledge execution. Again, our intuition here is we want to make the right session execution independent of the left session. So what we do here is that we focus on the value. This is the final output of the verifier. It's a binary bit indicating if the verifier accepts or not. And here we have this simulator. Again, the simulator is not rerunning the verifier, but it could internally run the machine M and do some task to help him to force the verifier this again honest verifier to output the B that is computationally indistinguishable from the real world execution. The intuition is whatever the man-in-the-middle can do here. Now it could be done by the simulator without the help of the left honest prover. So that means the man-in-the-middle S3 cannot prove any statement that cannot arrange it, meaning without help of the left communication. That's our those are our definitions. And before going on, I want to say that these two notions, non-malleable COM and ZK, they are pretty useful. A non-malleable equipment has been helped us to reduce the round complexity of MPC protocols, and also the non-malleable zero knowledge give us a better concurrently secure MPC protocols. So let's look at the state of the arts. For on the theoretical side, things are very beautiful. After long research, we eventually get the constant round constructions from the minimal assumption of one functions. In practice, we do have a very efficient construction for non-malleable equipment. It's a BGRV15 protocol. This is a CCS paper. It actually implements an earlier result by GRRV. It is based on DDH. It gives you a very fast implementation. However, the situation for non-malleable zero knowledge is less satisfactory. There's basically no reported implementations at all before this work. For those who are familiar with the literature, you may realize that, okay, there is a standard transformation going from non-malleable commitment to non-malleable zero knowledge. It's simple. You just ask prover to commit the witness using a non-malleable commitment. And then you just use a standard zero knowledge to prove that the committed value is indeed the valid witness. For this protocol, actually the first step is can be done very fast. For example, you just use the BGRV15 as your underlying implementation. But the issue happens at the second step because you are proving something about a non-malleable equipment. This non-malleable equipment is very complicated. It's not like as small as NAR. It has a large circuit implementation. And if you want to do that, it takes, for reasonable parameters, it will take more than 3 minutes. So that's basically the current situation. So our result here is that we give the first practical NMZK protocol in the appellate model, meaning without any setup. And we only need symmetric key assumptions, basically one function plus clearing recent hash. Also, our technique also implies the first practical non-malleable equivalent. That is from symmetric assumption only. This is in contrast to the previous BGRV paper I mentioned, which is based on DDH. Yeah. Now, in the following, I will talk about our techniques, and but the organization is like this. We first build I will first describe a new template for non-malleable zero knowledge protocol. If you just care about impossibility results, there are several ways to do that. But we'll show you a specific one that has the potential to be implemented efficiently. Once you have this template, we will identify the efficiency bottlenecks if you want to implement it. And then we will show some new ideas to deal with the bottlenecks and eventually get an efficient protocol. Here comes the catch. We started with a non-malleable zero knowledge protocol. But because of the new ideas we use to make it efficient, at the end, we lose non-malleability. So we only managed to prove that it's a simulation sound zero knowledge. I won't define this notion formally here, but I just want to mention that this is a very useful notion. It's incomparable to non-malleability, but I will say for 99% times, as long as non-malleable zero knowledge works, you can replace non-malleable zero knowledge with simulation sound zero knowledge, and it will still work. But anyway, as long as you have simulation sound zero knowledge, there are standard transformations to make it to give you non-malleable ZK and also non-malleable commitment and preserving the efficiency. So let me start with this template. This construction actually is very simple. First, the verifier commit to a random string of the length of a security parameter, use the extractable commitment. Next, the prover commit to a string sigma prime using the ENMC. ENMC is basically a non-malleable commitment scheme, but it is also extractable. And next, the verifier will decommit the sigma he committed in the first stage. And eventually we give a statistical WIOK, a witness distinguishable argument of knowledge, where the prover proves that, okay, I know the witness of the statement I'm trying to prove, or I actually set sigma prime to be the value of sigma the verifier committed before. This paradigm, it looks, everyone should be very familiar with this. It just looks very familiar, similar to Fagay-Shamir or FIOS paradigm. So the intuition here is the verifier set up the trapdoor. And if you are able to learn this sigma somehow and commit sigma prime equals sigma, then you don't need to do this part honestly. You don't need to know witness. You just use the trapdoor. That's actually how simulator works if you want to prove this protocol is their knowledge. But for Slanist, we know that a malicious prover will never learn this sigma before the verifier commit. So it's done. We've seen this kind of structure a lot of times, but here are the main differences for this stage. We are using the non-malleable commitment, and this is actually what bias non-malleable zero knowledge. So I don't want to get your lunch delayed, so I'll give you one-page security proof showing mainly the intuition. So intuition here is this is nothing but the man-in-the-middle execution of our protocol. What we want to show is the right execution and the left execution, they are independent. So what we do is we want to make the left communication independent of the witness. And meanwhile, we make sure that the adversary commits the verifier with the same probability. If we manage to do this, that means the right communication, that means the left communication doesn't help at all, right? So to do that, we're just doing what you would do for Fagay-Shamir zero knowledge. We extract the trapdoor and then commit to the trapdoor instead of all zero strings. Previously, the honest prover using witness. Now we have the trapdoor. We switch to the trapdoor witness. So there is only like one point I want to mention actually. The only risk for doing so is we are extract trapdoor and commit to it in the left session. However, nothing stops the man-in-the-middle adversary to perform the same thing in the right session, right? He could also potentially extract the sigma tilde and commit to sigma tilde. If he is able to do that, you cannot say he's using the W tilde in this stage, right? So, but this is actually exactly what a non-malleable commitment captured in the second stage. The non-malleable commitment definition tells us that if we switch the value of sigma tilde, sigma prime, the man in the middle cannot switch the value he committed here. Otherwise, that means his value committed here is dependent on the value we commit in the left. So because of this, because of the non-malleability of this commitment stage, actually we can do this change, but man in the middle cannot. So his probability of committing the verifier in the right won't change. So now here comes the real meat. I will talk about how to make this protocol efficient. If you stare at this protocol for a few seconds, you realize that there's only two efficiency bottleneck. The first one is this non-malleable commitment stage, and the second one is this a statistical WIOK. We'll address them one by one. We'll start with the last stage, this protocol. First, I want to say that you see it has two states. It's our composition of two statements, right? But for the first statement, this is something you have to do because at least a non-malleable zero knowledge is a zero knowledge. Your goal is to prove a statement. This is the price you have to pay. However, the second part of our statement is something by us non-malleability. So we should like make his cost as small as possible. So the naive way to do that is okay, I just view this as an NP statement and use the state-of-art fast zero-knowledge implementation. For example, the Ligero protocol by HIV. This turns out to be slow for the same reason because this statement this statement is actually about the non-malleable commitment, which has a large subject description. So our solution here is try to use the OR competition technique developed for Sigma protocols originally by CDS94. So let me briefly recall the definition of Sigma protocols. For now, I would just say it's a 3-round public coin protocol. It's honest verifier, your knowledge, and it's also WI And I know that we have extra requirement, for example, special soundness, but it's not that important for this talk. Okay, so let's ignore that for a little while. So the CDS technique is for to give you an efficient way to prove OR composition statement of this form. So if you want to perform this task, the naive way is just view X or X prime as a single instance and run the original protocol, right? But that could be, I mean, that could be large. You need to reduce this OR composition to NP statement, and that could blow up the size of the statement. So CDS is an alternative way to do that. It basically allows you to do that with a cost of 2 times the Sigma protocol for a single statement at most. So what the prover do here is actually, you can think this as 2 parallel execution of the Sigma protocol. For now, let's assume this is a witness for X. To prove this OR statement, you just need to know 1 witness, right? So in the left session, the prover play honestly using witness W because he has witness W. Then in the right session, the prover is going to use the honest verifier simulator. So to use the honest verifier simulator, so the simulator will want to sample the challenge or public point challenge string, right? But if you just do it naively, like meaning you ask the verifier to give you beta and beta prime, then you don't have, you cannot use the beta prime chosen by the verifier. So what should we do now? The idea is that we just combine these 2 challenge string, beta and beta prime, to be a unique string and ask the verifier to sample a unique string to the prover. The prover, we give the prover the choice to decompose it as an XOR of 2 random strings. So in this way, actually the prover can run the simulator for the red session first, and the simulator will sample beta prime, and you will just use that beta prime as a share here, and then the remaining share beta can be computed as a beta prime X or beta hat, which is the random string chosen by the verifier. And in this way, you lose control of beta, but it's okay because beta is the part you're gonna, beta will be viewed as a challenge for the left interaction for which you have the witness. You can answer any challenge. So that's how this OR combination idea works. And as you can see, the only cost you pay is actually the proof for the left session. For the right session, you are running a simulator. If you pick some particular Sigma protocol which has a very fast honest verifier simulator, this protocol could be very fast. And that's what we do. Here is our OR combination statement. And we will pick this Ligero as our underlying Sigma protocol and implementing this idea. So your cost will be just the proof for the first part of the OR statement, which is something you cannot avoid, right? And the simulator, okay, to give you more information, HIV is based on a zero knowledge PCP and then following the Killian approach. For this kind of a PCP-based protocol, it's slow if you want to generate the PCP, but it's easy to simulate. It's nothing but just a random openings of Merkle tree path. Right? So that's very fast. Okay, here I want to mention caveat. What I said, it looks very, it sounds very good, but however, Ligero protocol is not a Sigma protocol. The main difference is the Sigma protocol is 3 round. It has basically 1 challenge response slot, beta and gamma. But Ligero, actually, it has 2 challenge slots. You can think it's fixed alpha, then beta 1, gamma 1, beta 2, gamma 2. For this kind of protocols, it kind of well known that this CDS OR combination doesn't work. Especially, like, I think people working in signature, they will face this problem. But in this work, we do develop the method. It's kind of general to deal with multiple challenge response slot protocols. How do we do OR combination for them? But unfortunately, I won't have time to talk about that. You can check our paper for details. But that's the main idea how we make this last stage efficient. Let's say OR combination. Next, the ENMC stage. First, I need to open this stage and show you the structure. This is the construction by BGRV, and you don't need to understand what it's doing. I just want to show you the structure. It's nothing but the committer commit to some field elements, and then the receiver send the challenge, which is also field elements, and then the committer the committer just responds with again a few elements. Finally, you prove some inner product relationship. So for this structure, why PGRV is fast? The reason is they pick algebraic assumptions and take advantage of that. For example, their commitment is some kind of variant of L gamma encryption, and their zero knowledge is basically Schnorr's identification scheme or Schnorr's zero knowledge. So these two things go together very well. So they eventually have a very fast implementation. But now we only want to use symmetric assumptions. The naive way to do that is you just replace all the commitment, use AES-based commitment, then you use Ligero general purpose ZK to do this proof. Again, very slow because the circuit size is large. So our idea here is we want to reduce the new problem to the one we've already solved, right? So we just show how to make this part fast by our composition. Can we reuse the idea here? At first glance, it's unclear because this is not an OR statement. It's just this stage we call it proof of consistency. It's just a zero knowledge proof. There's no other OR statement. But to reuse the idea, just augment it. Let's say this is a non-malleable commitment scheme. Now we additionally give the committer a witness and a statement pair, and we modify this ZK argument to prove the original consistency condition, and also this is the OR composition. You just prove X in the language. So if we give the committer the choice, if you have witness, you don't need to behave honestly here. You can cheat, as long as you can use this witness. Otherwise, if you don't have witness, you just do everything honestly. You can still finish this as the original ENMC. So now I make it OR composition, so I can use the original approach. Here, as I said before, the committer has a choice, right? If the statement you are going to prove is large, then maybe if this statement is even larger than the original consistency condition, then you just actually you don't do this. You just prove the original consistency condition. But this structure will give you benefit if the statement you want to prove is small. I mean, at least smaller than the original condition. Now the efficiency of the accommodation will kick in. Okay, that's we summarize this as a new primitive called the instance-based non-malleable equipment. Instance means this statement witness pair. So that's the idea. But as I said before, there's a catch. If you do this, previously this is a non-malleable equipment. However, now if the X is true, the true statement here, you don't know if the minor middle adversary has a witness or not. However, as long as the X is true, the minor middle adversary has the potential to use some witness. So that means this non-malleable equipment may not be performed honestly. So it may not be non-malleable at all. Because of that reason, we cannot show it's a non-malleable equipment, but we can show that it's a simulation sound. So what do we get so far? The simulation found sound zero knowledge. And as I said earlier, there are standard transformations to make it non-malleable ZK and non-malleable commitment. You don't need to know how it works and why it works. We just want to focus on efficiency, right? So bottleneck is the final stage. How do we solve it? It's OR statement. So same idea as before. And yeah, here I want to show some numbers. This is you run our non-malleable zero knowledge protocol on a SHA-256 instance, and this is a non-malleable equipment committing to a single bit. The main takeaway here is we are not trying to provide a off-the-shelf solution. I just want to show you that non-malleable zero knowledge can be within the reach of practical computation. So we didn't try much harder to push this number smaller and smaller. It's just a demonstration concept, I would say. That's all I want to share, and I'm happy to take questions.
Are there any questions?
I start. I just want to compliment your list of references because I didn't see it. Can you hear me?
Sorry, can you
Sure.
repeat?
Yeah, it's good.
So Euroclip 2003, we had something we call Omega protocols, short extension of Sigma protocols, which achieve non-malleable zero knowledge. And they're in the CRS model. So,
I see.
but at the time was the first sufficient non-malleable zero knowledge protocol after clause. And we
I
use
see.
also the OR composition trick. And yeah. So
I
you
see, I see.
so check it out.
Yeah, the
So
issue is I know the I
Omega
know the title of your paper, but I never read it. So I will go back and read it and give you the updated version.
Yeah, so by efficient, we don't mean, we don't want to implement it. But
Yeah, yeah, yeah.
at the time, the only thing that was available was clause, right? So
I see, I see.
we also go through simulation soundness.
Cool.
All right. Thanks.
And the situation is we are mainly focused on like the plane model. Yours are in the CRS model, but you are right. I need to give you the reference because I also like survey all the existing constructions in the CRS model and in the random oracle model. Yeah, but I just want to mention that in a CRF's model, if you get non-malleable primitives, it's hard to use when you want to do composition. For example, UC, yeah, you need to program CRS. Maybe your larger protocol already programmed this kind of things. Yeah, but I will set your paper.
Is there any other question? All right, let's thank the speaker again.
Thank you.
And this is the end of the session.